So here is question number 16. Up to what distance is ray optics a good approximation when the aperture is 4 mm wide and the wavelength of light is 800 nanometer? Now we know very well that the ray optics is good approximation up to Fresnel distance only. Since we know that ray optics holds good approximation till Fresnel distance, and this Fresnel distance is given by ZF, that is equal to A square divided by lambda, where A is the size of aperture given here, lambda is the wavelength of light, this is also given here. Plugging the values, A is 4 into 10 to the power minus 3 whole square, whole divided by lambda, that is 800 into 10 to the power minus 9. After solving, we will get the Fresnel distance ZF, that is 20 meter. So therefore we can say that the ray optics in this case will hold good up to 20 meter. Here ray optics hold up to 20 meter. So after looking the options, we can say that we'll have to go with option number 1, which is absolutely correct. Now let us proceed to the next question, that is question number 17. So here is question number 17. In Young's double slit experiment, a mica plate of refractive index mu is introduced in the path of light coming from one of the slit. If the central bright fringe shift to the point originally occupied by fourth bright prism, then thickness of mica plate will be what? Now we know very well when a mica plate of thickness T and refractive index mu is introduced in the path of one of the source of light, then fringe shift occurs, and this fringe shift is given by the expression d times mu minus 1 T by small d. And here in this case the shift is from 0 to fourth bright prism, means from principal maxima to fourth bright fringe. So here the shift we can write 4 lambda d upon d. After solving, we will get the thickness T as 4 lambda divided by mu minus 1. So this will be the thickness of mica plate. And after looking at the option, we can say that option number 3 is absolutely correct. So we'll go with option number 3. Now let us proceed to the next question, that is question number 18. Here is question number 18. The critical angle for transparent crystal air medium is 60 degree. Then its polarizing angle will be what? This question is actually the combined application of Snell's law as well as Brewster's law. According to Snell's law, we know the expression for critical angle sin C equals 1 by mu, where mu is the refractive index of denser medium with respect to rarer. Mu therefore equals 1 by sine critical angle 60 degree. So sine 60, we got the refractive index of the medium, that is 2 upon root 3. Now the polarizing angle according to Brewster's law is given by IP, that is tan inverse mu. So tan inverse mu is what? 2 by root 3. So the polarizing angle we have got IP equals tan inverse 2 by root 3. Now after looking at the options, we can say that option number 3 is absolutely correct. So we have to go with option number 3, tan inverse 2 upon root 3. Now let us proceed to the next question, that is question number 19. Here is question number 19. In a forward bias PN junction diode, we are having 4 options. Net current in the diode is only due to diffusion. Net current in the diode is only due to drift. Net current is sum of magnitude of diffusion current as well as drift current. And the last option is net current is difference of magnitude of diffusion current and drift current. We know very well in case of PN junction diode, diffusion current flows from always P to N. On the other hand, drift current flows from N to P. So we can say that this diffusion and this drift current, they are flowing opposite to each other. Now, in case of unbiased condition and at steady state, the diffusion current equals the drift current in magnitude and opposite in direction. So that's why I net will be 0 in case of unbiased condition. On the other hand, in case of forward bias condition, the width of depletion layer reduced. So that's why the diffusion will be diffusion will be fast and diffusion current will be increased. So net current will flow and it will be the difference of diffusion current as well as drift current. So we can write unbiased condition under the steady state, magnitude of diffusion current equals magnitude of drift current, and they are also opposite. Therefore, I net will be 0. On the other hand, in case of forward bias condition, diffusion current increases. So, I net we can write magnitude of diffusion current minus of magnitude of drift current. Drift current almost remain constant in case of forward bias. So that's why the net current we will get subtraction, or you can say difference of diffusion current and drift current. So looking at the options, we can say that we have to go with option number 4, which is absolutely correct. Now let us proceed to the next question, that is question number 20. Here is question number 20. Question belongs to the section logic gate. Which logic gate is represented by the following combination of logic gates? So let's say here you can say A is connected with NOT gate and B is also connected with a NOT gate. So as output you will get A bar. Output of second NOT gate you will get B bar. The third gate you will see as a NAND gate, and finally the output of NAND gate is given by Y equals A dot B whole complement. So here the input you can see A bar and the input is B bar. So A bar, B bar, and according to NAND operation you will get the output whole complement of AND of both inputs. So that's why this output you will get. Now you can apply the De Morgan theorem. According to De Morgan theorem, A bar dot B bar can be replaced as A or B whole complement, and there is another complement. Complement and complement, they will cancel each other. So ultimately you will get the output Y as A or B. So actually there is the OR operation. This whole gates, this combination is giving you output of OR operation. Behave like an OR gate. So that's why we will go with option number 1, which is absolutely correct. Now let us proceed to the next question, that is question number 21.